60.2% of the supply voltage is around 5.7 V. We will use a stopwatch and charge the capacitor until the value reaches 5.7 V. Stop the watch and note the reading of time in seconds. For more details, check the example given below the instructions. Now, let's see how to find the value of a capacitor by measuring the time constant. Note, an oscilloscope will do this better with precise value instead of multimeter. Make sure to disconnect as well as discharge the capacitor from the board. Connect a known value of resistance, e.g. 510 k ohms resistor, in series with the capacitor. Apply the known value of supply voltage, e.g. 12 V or 9 V, to the capacitor connected in series with a 10 k ohms resistor. Now, measure the time taken for the capacitor to charge about 63.2% of the applied voltage. For instance, if the supply voltage is 9 V, then 63.2% of this is around 5.7 V. From the value of the given resistor and measured time via a stopwatch, calculate the value of capacitance by time constant formula, i.e. tau equals tau, time constant. Now compare the calculated value of capacitance with the value of capacitor printed to it. If they are the same or nearly equal with, the capacitor is in good condition. If you find a noticeable difference in both values, time to change the capacitor as it is not functioning well. Example, suppose, we are going to test a 16 V, 470 μF capacitor. If the supply voltage is 9 V, then 5.7 V is 63.2% of the supply voltage. We will connect the capacitor to the battery for charging and start the stopwatch. When the meter shows a 5.7 V, we will stop the stopwatch. Suppose, the stopwatch shows 4.7 seconds of time duration. Now, use the time constant tau equals RC formula for measuring the capacitance, i.e. C equals tau / R. C equals 4.7 seconds / 10 k omega. C equals 0.47 mF equals 470 μF. Now compare the calculated value of the capacitance with the value of the capacitor printed on it. If the calculated value is nearly equal or having a difference of plus or minus 10 to plus or minus 20 to the desired capacitor, it is a good capacitor. If the calculated value is far away with a noticeable difference, the capacitor is faulty. In our example, the calculated value is almost the same as the actual value of the capacitor. It means the capacitor is in good condition. The discharge time can also be calculated. In this case, the time taken by the capacitor to discharge to 36.8% of the peak voltage can be measured. Good to know, the time taken by a capacitor to discharge about 36.8% of the peak value of the applied voltage can be also measured. The discharge time can be used as the same in the formula to find the value of the capacitor. Method 6. Test the capacitor by continuity test mode. In the DMM and AVU meter, the continuity test mode can also be used whether the capacitor is good, open or short. To do so, follow the simple instructions below. Disconnect the power supply and remove the capacitor from the circuit board. Fully discharge the capacitor using a resistor. Rotate the knob and set the multimeter in continuity test mode. Make a contact of the positive, red, probe of the multimeter to the anode, plus, and common, black, probe to the cathode, terminal of the capacitor. If the multimeter shows a sign of proper continuity, beep sound or LED light, and suddenly stops and shows an OL, open line, it means the capacitor is in good condition. If the multimeter doesn't show a continuity sign with beep or LED, it means the capacitor is open. If the multimeter LED lights on and makes a continuous beep sound, it means the capacitor is short and it should be replaced with a new one. Method 7. Test the capacitor by visual and apparent checking. It is the basic approach to determine the defective capacitor without a multimeter by observing the apparent signs appearing on it. The capacitor is failed and damaged if you find any of the following conditions. Bulging top vent of capacitor. The top vent of the electrolytic capacitor in shape of K, T, or X are the weak points made to release the pressure during the failure of a capacitor to avoid serious damage to the surrounding and any other components connected near to it. If you find a bulging top of the capacitor, it is the electrolytic discharge, black, white, orange color, which depends on the electrolytic material, i.e. the capacitor releases a gas pressure during failure and breaker the top vent of the capacitor. Bulging bottom and lifted case of capacitor. If the produced gas pressure does not break the top vent of the capacitor during failure, it goes through the bottom and pushes the rubber, which makes the bottom bulge and lifts the case. Testing SMD and ceramic capacitors. If you find the following signs on ceramic or tiny SMD capacitors, they are faulty and need to be changed with the correct ones. Broken or cracks in the casing. Damaged or any sign of burnt casing. A hole in the casing. Method 8. Traditional method to test and check a capacitor. Note, not recommended for everyone but professionals only. Please be careful to do this practice as it is dangerous. Make sure that you are a professional electrical engineer/electrician and you really know that you are doing something hazardous. Please follow the safety precautions and warnings before applying this method. This is only applicable in an emergency, where replacing the capacitor with a proper value is important, and there are no other options to check the damaged capacitor. Because serious damages may occur during this practice. If you are not sure, because serious damages may occur during this practice, follow the other options, 1 to 7, as alternative methods to troubleshoot the capacitor. Suppose you want to check the capacitor, for example, fan capacitors, room air cooler capacitors or tinny capacitors in a circuit board/PCB, etc. Warning and safety precautions for testing a capacitor by method #8. For proper safety, use a 12 to 24 V DC source in case of both polar and non-polar capacitors with a 1K ohms 10K ohms, 550W resistor. The resistor should be connected in series with battery and capacitor positive terminals. This way, it will reduce the excessive current while charging the capacitor. In case of absence of DC source, like batteries, the high-rated capacitors, i.e. fan capacitors rated for 3.5 F, 120, 230 or 400 V, you may use 120-230 VAC, but you have to connect a series of resistors, say 1K ohms 10K ohms, 550 watts, to connect between capacitor and 230 VAC supply. This way, it will reduce the charging and discharging current. Here is the step-by-step tutorial on how you may check a capacitor by this method. Disconnect the suspected capacitor from the power supply or make sure at least one lead of the capacitor is disconnected from the PCB board. Make sure that the capacitor is fully discharged. Connect two separate leads to the capacitor terminals. Optional. Now safely connect these leads to 24 VDC or 230 VAC supply for a very short period, about 1 to 4 seconds, or for a short time where the voltage rises to 63.2% of the source voltage. Remove safety leads from the 24 VDC/230 VAC supply. Now short the capacitor terminals. Please be careful to do that and make sure that you have worn safety goggles. If it makes a strong spark, then the capacitor is good. If it makes a weak or no spark at all, then it is a defective capacitor. You would have to change it immediately with a new one. Note, keep in mind that a polar capacitor should not be connected to the AC supply. On the other hand, a nonpolar capacitor can be attached to the DC supply because they are back-to-back electrolytic capacitors. As we know that capacitors block DC but let pass the AC, but still it will charge with the DC supply source until it reaches the terminal voltage level. In short, nonpolar capacitors can be operated on both AC and DC supplies, while polar capacitors only operate on DC. For more details, check the previous important post on what happens if we connect a polar capacitor the wrong way.